So who in the room has actually used hardware transactional memory? You've used, where did you use it? Sorry?
I've used something similar on PowerPC, the Reg Fabric registers next time.
Okay. You've used the Intel? Haswell, okay, right. Cool, so we got 2 people for the recording, I think, unless I missed someone. So hopefully I can give you some decent education of transactional memory. So I'm going to talk about what transactional memory is, a bit of a hardware and software overview of it. Then I'm going to dive a little deeper into the architectures that currently exist that implement hardware transactional memory, and then some of the usage at the end. So, transactional memory. So if you've got a multiprocessor system and you need to do something like increment a count, this is sort of a pseudo-assembler, you need to provide some sort of mutual exclusion between when you're accessing variables or when you're writing variables. And so here we've got a load, add, store. We're just incrementing a value count. You can't do this on multiple processors at the same time without having some sort of mutual exclusion here. So at the top, we've got an acquire lock, and the bottom, we release the lock to make sure that only one person is in this critical section at a time. And this kind of works okay for a count. There's plenty of other ways to do this. But say you've got something bigger. Say you've got like a big tree data structure, some large data structure. Acquiring a lock on that data structure is obviously not going to work particularly well if lots of people are hammering on that tree in different parts. So what you might decide to do is something like fine-grained locks, obviously. So if you're just editing this part of the tree or this part of the data structure and I'm just editing this part of the data structure, then we can kind of work at the same time and not override each other. So you do something like this, you acquire a lock on a subtree, change your subtree, and then release the lock on your subtree. And this kind of works okay, except you have to statically partition it up when you're writing your program normally. And there's a whole bunch of other mechanisms. There's Paul's RCU, obviously, sequence locks, reader-writer locks, a whole bunch of other stuff. So what is transactional memory? Well, it's a new concurrency primitive. It's a new sort of atomic operation. And you can do this. And you can actually do this in GCC 4.7 today. It will fall back to a software mechanism of doing transactional memory, unless you've got hardware support. GCC actually compiles down to the hardware primitives. But you can do this today with GCC 4.7 and above. And this count will be atomic and other processors won't be able to see it. You won't be able to race with each other. Not a very interesting example, but here's another example. Say you're doing a financial transaction where you're transferring $5 from Alice to Bob. You can do something like this. You might want to check that Alice had $5 first, but whatever. So all you have to do is basically take $5 off Alice, add $5 to Bob, simple as that. And someone looking at this will either see both of those changes or neither of those changes. They won't see something in between. So transactional memory is a way for the hardware to dynamically determine where shared data is. So if you're, say, operating on a large tree structure, if you're operating over here, one CPU is operating over here, another CPU is operating over there, well, the hardware can actually work out, hey, you're not actually colliding at all, so we'll actually opportunistically just let you guys run. It's kind of an optimistic versus a pessimistic way of doing it, so that the hardware goes, maybe you can actually run and we'll try, and if you don't collide, then we'll just let you go through. Versus a pessimistic way where you have to take a lock and you have to wait your turn and blah, blah, blah. Dave Boucher used this analogy last year at this conference. It's kind of like traffic lights versus roundabouts. Traffic lights is kind of the old mechanism of you have to wait for your green light and then you can enter the intersection, but the intersection's all yours at that point, and then while other people are waiting. Where roundabouts are kind of, everyone kind of comes in and has a go, and hopefully you can get through sort of in a dynamic fashion. So transactional memory is kind of advertised like this. It's you program with coarse grain. You only have to start a transaction. It's the programming of coarse grain, but with the performance of fine grain. And this sounds fantastic, right? Obviously, some of us are a little bit more pessimistic than that. So what does this look like in our pseudo-assembler? Well, it looks very similar to what it did with our locking. So we begin a transaction, we do our load, add, store, and we end our transaction. And anyone doing the same thing on a different CPU won't be able to race. We'll be able to see any collisions between the two. Maybe it becomes a little bit more interesting with our transferring money from Alice to Bob. You've got 2 loads at the top, load the 2 accounts, add to one, subtract from the other, and then store both of those. So there you've actually got two stores, so you will only see, someone doing the same code will only ever see both of those stores or neither of those stores. Great. So this sounds fantastic, right? In reality, we know this is not true. So transactions sometimes fail. So what happens? So similar example, the same example again with the increment count. But now we have this abort handler at the bottom, and some of you may not be able to see that. The abort handler, basically anytime you're running through this, the CPU is running through this load, add, and store, it may decide you've done something dumb, it may decide that you're conflicting with someone else, and at any point in the flow there, it may decide, I'm going to need to roll back, I've got a collision, I'm going to roll back, and it will roll back and head to this abort handler, and all of the state will be wound back to where it was at the start of the transaction. And here in our abort handler, we're just retrying. So in the end, we have to provide an abort handler. Unfortunately, all but one particular architecture in one corner of the architecture, which I'll talk about later, don't provide any forward progress guarantees on if you just keep running this transaction. So you may just keep running it over and over and over again, and you'll never actually pass. So you can't just retry forever. So you end up having to fall back to locks anyway, which is kind of annoying. It could be okay. You may end up, that lock may just be a simple coarse grain lock. It might be okay because you might not actually hit, that may not actually become a bottleneck, but it might. So it can be hard. So that's kind of a vague software overview. From a hardware perspective, how do CPUs do this? The first thing they have to do is they have to detect collisions. There's a whole bunch of things they have to do, but this is sort of a high level thing. First, they have to detect collisions between transactions. And if it detects a collision, what it needs to do is, so if it doesn't detect a collision, it can just keep going through using these speculated values, and it will then commit those values, and that's all great. If it does detect a collision, then it needs to roll back all the state and go back to this checkpointer state that it's kept around. This actually works pretty well in modern processors. They already have caches, they have L1, L2, blah, blah, blah. And when you write values, you tend to write to the cache rather than directly to memory. So it's fairly easy to add this, not really easy, but it's readily shoehorned into modern CPUs by just keeping the data stored in the caches. A couple of things you do need to add, obviously, are you have to have a read-only set. So when you've started the transaction, the hardware needs to keep track of everything that you have read inside that transaction. Every single cache line that you've potentially read, or that you have read. It also needs to keep a separate set of cache lines that you've written to inside that transaction. Now, if two CPUs have two transactions running at the same time, their read-only sets can actually overlap, and that's perfectly fine. Say you're looking at your tree structure and the two transactions had to start at the top and had to move down looking at that tree structure when they're both reading the top node, so that's okay. But when you get down to the bit where you do the writes, they must not collide with either another write or another read. So if someone's writing that top node, then you're in trouble. So this is all sort of implemented in the caches. Unfortunately, obviously, it's limited to the cache size, which is okay, except if you've got CPUs that share caches, or on Power, we have fairly highly threaded processors. POWER8's SMT8, so that basically splits your cache in 8 to make your maximum transaction size. So that's a problem. It's limited to cache line granularity. So if you just happen to have two pieces of data that are on the same cache line, but they're being used on two different CPUs and you're writing it to two CPUs, then you'll get some false sharing. In reality, that may not necessarily be a problem, because if you're writing two variables on two different CPUs that are in the same cache line, you don't want to do that from a performance perspective because you're going to be thrashing that cache line. So you probably want to separate them anyway from a performance perspective. But that would be a performance problem in the past, and it will be a transaction failing problem now. Implementing these in the caches also has a problem with cache associativity. So if you have, like a modern processor has an 8-way set associative cache, let's say, that means one piece of data in memory can only go in 8 possible cache lines. if those 8 cache lines are already full of transactional data, it's already in your read or write set, then it can't go in there and you'll end up overflowing your buffer after just 8 cache lines, which could just be 8 pieces of data. And this isn't necessarily a cache problem, but it's also, you can't do something invalid. You can't sleep in the middle of a transaction. There's a whole lot of things you're not allowed to do inside transactions. Otherwise, you'll get aborted. So what happens when the hardware needs to roll back? So there's two things that the hardware needs to do. One is the transactional memory footprint. And this is, we've already talked about this, we already have this stored in the caches. If it needs to roll back, it can basically just invalidate those cache lines. They won't participate in cache coherence or cache intervention. So that's actually fairly easy. The second thing that you need to do is the register set. These are your GPRs, floating point registers, all that sort of stuff has to be rolled back as well. Again, this works fairly well with modern processors, with modern superscalar out-of-order processors have register renames. So you have far more physical registers than you do architected registers. And so that means that, since you've got far more physical registers, the hardware can just keep those registers around and it doesn't have to worry about it until the end of the transaction. It knows it can go and commit it. Screw that. So another interesting piece from a hardware and a software perspective is nesting. From a software perspective, it's really important that a transaction may correspond to a lock, and we already know that a lock, you may actually want to take multiple locks at a time. So how this would happen in transactions is you would actually start a transaction, and then before ending that transaction, you would start another transaction. So they're essentially nested inside each other. So this is important for software from taking multiple lock perspective. It actually turns out to be pretty easy to implement in hardware because you can implement it as just a single level. And if any of the inner transactions end up aborting, you just roll back to the outermost transaction. So let's look at some of the architectures that we have at the moment. So we have Intel's x86, IBM's Power, and IBM's S390. So Intel in Haswell have introduced their transactional synchronization extensions, and this comes in 2 flavors, which is the restricted transactional memory, which I'll talk about immediately now, and hardware lock collision, which I'll talk about later on. So restricted transactional memory, it comes with 4 basic instructions. Xbegin starts a transaction, Xend ends a transaction, Xabort will explicitly abort a transaction if you need to, and Xcheck checks to see if you're in a transaction. Simple. So that looks like this in x86 assembler if we're doing an increment count. Of course, you would never do an increment count like this in reality. This is just an example, and I'm terrible at x86 assembler, so just consider this pseudo x86 assembler. But basically, you have your Xbegin at the top, and you register your abort handler directly with the Xbegin. And basically, you come in here the first time, and you won't take off to the abort handler, obviously. You come in transactionally, you do your load or your move, increment move, and then hopefully you hit the end and that will be committed, or anything that was in that critical section will get committed to memory and other people can see that. If there is some sort of conflict or abort in the middle here in this move, increment, move, at any point in there, the hardware can say, okay, something's gone wrong, something, whatever. It roll back all of the state back to the start and branch off to this abort handler at the bottom. Now the abort handler is pretty dumb here, it's just branching back to the start and just doing a retry. So on PowerPC, what does this look like? Well, in PowerPC, PowerPC is what I work on. So on POWER8, we are introducing transactional memory. And this comes with 4 basic instructions, which is tbegin, tend,tabort, and tcheck. Exactly the same as x86. And it looks like this, which looks very similar to x86, except tbegin, you don't register your abort handler. We've got a fixed instruction width, so having to put the address in the instruction would use up a lot of opcodes. So what PowerPC does is it sets a condition flag based on whether you're transactional or not. And so the next instruction, this BNE abort handler, is simply a conditional branch. And so the first time through when you're transactional, it doesn't take that conditional branch. You do your load, add, store here, and hopefully you commit the transaction at the T end. Again, at any point, if you abort, you have any sort of abort, you end up anywhere in here, the hardware can just roll back and decide, I need to go back to the abort handler. And it'll roll back all of this state that you have, and you'll end up, and the abort handler just does a retry. So S390, this is one of my favorite photos from IBM Centenary 100 years ago. It spans the whole 100 years of IBM with Thomas Watson Jr. on the left of the Watson family who started IBM, and it's his baby here, the System 360, which when he got the company, he bet the company on, he spent billions and billions of dollars developing the mainframe, the System 360, which is now still with us with the System 390 that you can still buy today. It's also a nice era when you kind of, when you had to be a stand-up member of society to use a computer, dress in a suit and a tie, and it wasn't really for us riff-raff hackers. So in S390, they're introducing transactional memory, and these are their 4 core instructions, which is tbegin, tevend,tabort, and etnd, which is extract transaction nesting depth. So if the nesting depth is 0, then it's a t-check. Simple. So it looks like this, which looks, again, very similar to the other ones. Tbegin, TDB, OXFF, you can ignore the TDB, OXFF for the time being. S390 is just like Power in that they set a condition flag or not based on whether they're transactional or whether they're aborting. And again, you go through here, load, add, store, and then hopefully you finish your transaction and you're done. And you can commit it all, make it visible to everyone else, or you jump back to your abort handler and you retry again. And I think this is kind of cool. We've got 3 separate architectures, all kind of developed independently, but they all end up kind of looking very, very similar at this sort of 10,000 foot view. So let's dig into some more specifics. So Intel's x86, one of the most important things we have is your abort codes. Why did you abort? And the most important one at the top is your transient abort. This is a best guess by the hardware to say, I think this abort was a transient problem. If you were to retry, it may actually work, as opposed to it was a persistent fault, which if you retry, it's not going to pass. It's a best guess by the hardware. It may not actually be able to tell you. And all of these bits, they can actually be set, multiple can be set at a time. So a conflict abort, obviously if you conflicted with someone else during a transaction. A buffer overflow, you overflowed your caches. Debug breakpoint, I'll talk about this a little bit later on. A nesting abort, say you aborted one of the inner transactions, you came back out again. And an xabort instruction. What you can actually do with xabort is you can give it a parameter, and so you can sprinkle your transaction with a whole bunch of xaborts, and when you abort, it'll tell you which one of those you hit based on that parameter. The thing I didn't talk about before was hardware lock collision. This is interesting. It's quite a bit different to the other ones in that it's backwards compatible. So you can use this on existing processors and it'll actually work. So how do they do this? So this is all x86. If you are trying to lock some critical section, you might do something like this, acquire lock with a mutex, and then do your critical section, and then you release your lock. Simple. In x86 assembler, it looks something like this. The top, I don't know x86 assembler very well, but basically the top is basically you exchange your mutex with your EX atomically. If your mutex is 0, no one has it, you jump into your critical section, you've succeeded. If it's not, you spin waiting for the mutex to be 0 and try again. Simple stuff. And the bottom is basically releasing the mutex down the bottom there, just set it back to 0. So the 2 things of real interest here are the lock, exchange, mutex, EAX. So this is basically trying to get and set the mutex atomically. And at the bottom is clearing the mutex. They're the 2 atomic operations. Now this is on old processors. This works today, pre-Haswell. What does HLE give us? Well, HLE, all you do is you add these 2 things, the X-acquire and the X-release. Now, X-acquire on processors before Haswell, X-acquire and X-release are just NOPs. So all it does is it falls back to the existing locking mechanism. On something that's got HLE like Haswell, what it does is it speculatively gets the mutex. So if the mutex is 0, it'll speculatively get it. It won't actually set it, but it'll put it in that read-only set so that if anyone writes it, we'll know about it. And it speculatively jumps into our critical section and then runs the critical section transactionally. So it does all the loads and stores, but it keeps it in its cache so no one else can see it. And then it gets to the X release at the end and it says, do I need to abort? And if not, if it actually can go through, it'll commit it all atomically at the end, at the X release, and it's great. If it hasn't, well, what about the abort handler? We don't have an abort handler here. Well, it actually turns out, obviously, that you have the abort handler built in. So you can just nop out the X acquire and X release if you can't do it transactionally, if the hardware can't do it transactionally, and it just falls back to the existing locking mechanisms. Cool. The problem there is obviously that's under the control of the CPU. I think in Haswell they say that they try once transactionally, and then if that doesn't work, they then fall back to the existing locking mechanism. But you can see that may not actually be a good idea. If the critical section is so big it's never going to pass transactionally, then why would you bother running it even once? So you can see them start adding heuristics as to, this critical section doesn't work very well, so let's never bother running it transactionally or whatever. So I think this will evolve over time to see how Intel approach it. So PowerPC specifics. So again, abort codes. We have this register, the transaction exemption and summary register, which is actually written by like this, which gives you a good idea of where this processor is developed. And we have a bunch of hardware causes. So there's a failure code with a persistent bit. We have a persistent bit instead of a transient bit. This is, again, a best guess by the hardware to say, we think this is persistent. If you try again, it ain't going to work. Footprint overflow, nesting overflow, self-induced overflow. You did something dumb, like you did a pause or something like that. You conflicted, so there's non-transactional and transactional conflicts. So a non-transactional conflict is you conflict with someone who's fallen back to, say, their locking mechanisms. They're not running transactionally. A transactional conflict is someone who's just running transactionally like you. So you get that fidelity of non-transactional or transactional conflicts. Translation invalidation, page got invalidated underneath you. Or instruction fetch conflict is another one. You can't write self-modifying code inside a transaction and then branch to that same self-modifying code inside the same transaction. You have to exit the transaction and then go and execute it. Too much crazy iCache, decache for the hardware to deal with. There's also a bunch of software causes, context switching. A facility unavailable is an interesting one. We do lazy floating point restore on PowerPC. So the first time you execute a floating point instruction, you'll trap into the kernel and the kernel will say, oh, you want a floating point, oh, here's all your registers, and it'll load them up and you can go. If you happen to do that inside a transaction, that will abort the transaction. This is a really good example of a transient fault because if you were to try again, you've now got all your floating point registers there and it'll probably pass that section. A signal delivered, an alignment fault, emulate instruction. This is a really good example of a persistent fault. If you have to trap into the kernel to keep executing an instruction, then it's going to keep aborting your transaction. So it'll set that persistent bit to say, I really think you're not going to pass ever. So don't bother retrying. We have this register, which is a best guess by the hardware to say, I think you aborted because of this instruction, which is handy. You have a nesting transaction level, which can tell you how far deep you are down. Now, interrupts are an interesting one. Interrupts, these are any sort of faults into the kernel, so interrupts, exceptions, faults. On x86 and S390, that will just cause a transaction abort. So you're in the middle of your transaction, you get a fault into the kernel, the hardware will roll it all the way back to the abort handler with all the state reversed, and the kernel will then see the user space state as of the abort handler. This is not what we do on PowerPC. What we do is we put it in what's called a suspended mode. So we don't roll it back, we keep it all there, and the kernel can then operate in the suspended mode. So what does that mean? So back at the start, I was talking about the hardware needs to keep track of two things. It needs to keep track of the transactional memory footprint and also the register set. When we go into suspended mode, the hardware is allowed to throw away the memory footprint. It doesn't have to, but it's an unbounded resource, and it might, if it's operating in a kernel, it might need to get some more cache lines. So it's allowed to throw away the transactional memory footprint. You can check to see if it's thrown it away by doing an xcheck instruction if you want, but it is allowed to throw it away. These are just any changes you've made. The register set it has to keep. This is a bounded resource. You know you've only got 32 GPRs or whatever. that's fine, and it has to keep that around. The hardware has to keep that around. Suspends don't abort, so suspended regions don't abort. This is just the region that's suspended. When you go back to user space, it can abort then. If you go back to user space, back to the transaction, it's allowed to abort then. But in the suspended region, it's not allowed to abort. So you can't be in the kernel in a suspended transaction and the kernel just aborts off to somewhere else. That wouldn't work. And the memory is persistent. The memory is non-transactional. This is not Matthew Wilcox's persistent memory. It means that it's non-transactional. So it will happen immediately. So if you're taking a timer interrupt, let's say, and the kernel's changing some kernel data structure, then that will be persistent. It's not going to be rolled back as part of the transactional memory footprint. So not only in kernel space can we do these suspended transactions, but they are explicitly exported to user space. So a user can say tsuspend and suspend his transaction and then do a whole bunch of stuff non-transactionally and then do a tresume. So this was our original PowerPC example. If we want to add a tsuspend and tresume to that, we end up with something like this. So we've got our tsuspend and tresume in here, and we may want to put some debugging output in there. Say I got here, just a little flag to say I got over here. Now these are exactly the same as the kernel ones in that you must, if you enter this suspended region, it must complete. So if you've got the load add store at the top in the increment count, we can be rolled back at any point there. The hardware can roll that back. It can do the load add and then go, stuff it, I'm going to abort. But once you get into the tsuspend, you have to execute every instruction until you get to the tresume. Does that mean you can't do a transaction in the kernel? No, you can do a transaction. You're asking about whether you have enough data there to context switch. You can save away the user context. You can save away this state in the context, and I'll talk about that in a second. So, but yes, you can use. So the question was, can you use suspend in the kernel? And yes, you can if you wanted to. Ben said our current implementation doesn't support that. So, where was I? So, the user suspend regions must complete. Once you get to the tresume, you can then roll back at that point. That's perfectly fine, but you can't roll back until you get to the tresume if you've already hit the tsuspend. So that's what I'm saying. User suspend regions must complete, much like the kernel one. Now, this has some interesting implications for context switching, because if you get a context switch in the middle of one of these, the kernel can't just automatically roll back all the state for you and go back to the abort handler. It must actually now go and save this speculated state and the checkpointed state and save that away somewhere. So this is a bunch of extra user space state, and this has implications for things like uContext. When you're doing a signal delivery, you have to have the extra set of state there stored on the stack, 32-bit, 64-bit, and you've got GDB would want to access this data, so you have to export it by ptrace. So there's a lot of other user space APIs we have to change. Sorry?
Is it really worth to go through all this?
Is it worth going through all of this? Yes. Yes, it is. We'll talk after. Anyway, we'll talk about that after. This also has implications for the stack. Stack is just like any other memory, but the problem is if you trash the stack when you're suspended, that will be persistent and you could end up corrupting it. So if you do something like this, where your tbegin is in a function, that's going to have some stack requirements. Your increment is fine. You can do that in a function and it'll get rolled back and that'll be part of the transactional memory footprint. But if your debug is in a function, that could write to the stack and that could corrupt the stack if you end up aborting at the tresume. When you roll back, the stack won't be actually rolled back to the right state.
It won't actually kill you anyway because the
yes, it will.
Yep. Will have created the stack to be transactional, put it in the right set.
Yeah, so Ben's saying, well, won't it kill you anyway? Yes, it will kill you in PowerPC and on S390. If you write to something in suspended mode, that's already been written to transactionally, it will kill the transaction explicitly. Yes, it will. But obviously it won't be.
Yeah, but you'll still be corrupted.
Yeah, you'll still be corrupted. Yes, you will still be corrupted. So, sorry, one thing I should say is here, this is not necessarily so much a problem for users because they can control it. Users can always do something dumb, right? But it is a bit of a problem for things like signals where the U context is written on the user stack, so you need to do things like use sig alt stack if you're getting asynchronous signals, and we do actually have a fix for this in the kernel as well. We have some S390 details with our gentleman computer user. Abort codes, obviously, they have some higher level abort codes, whether they think it's transient or it's a persistent or it's an unknown fault. And then a bunch of other good stuff. It'll tell you what sort of interrupt caused you to abort. You have a fetch and store overflow and conflict bits. The fetch and store is really interesting because this is kind of exposing these reads and write sets out to users. You can see if you've actually, which of those two sets you've actually overflowed. You've done a restricted instruction, your nesting depth, cache stuff. T-abort, again, you get all that sort of information. You can get a parameter out of that again. The tbegin register mark, when we did tbegin in the S390 example, I had the TDB OXFFF. The OXFFF is to say, which registers do I want to save? So you don't actually have to save and restore all of the registers. The hardware doesn't have to do that. And say you're going to branch off to a function anyway, which has got volatile registers, they may not necessarily care. So you don't need to roll them all back. We've got floating point. So that's another, if you care about floating point inside your transaction, you can say that. S390 also has this transaction diagnostic block, which provides a whole heap of information about the transaction to you. So you have this register, which is like the one on PowerPC, which tells you approximately what instruction caused the abort. You have a nesting depth. You can actually access through the TDB the checkpointed register set. So what was the register set at the tbegin? This is tbegin C. This is a different variant of tbegin, which is the one that provides some forward progress guarantees. Now you have to follow very strict limitations. You can only touch certain cache lines, and you can only execute up to 32 instructions. But if you follow those guidelines, you will be guaranteed to eventually complete, to eventually succeed. And you don't have to write an abort handler or an independent abort handler. And they have non-TM stores as well, like us. They don't have suspend and resume, like we have on PowerPC, but you can say, I want these stores to be persistent outside of the transaction. So, usage. So obviously, people won't care about the Linux kernel. That's why we're here. And internal locking, maybe. So what are we going to do internal locking? So Andy Clean's done a bunch of work on this. Linus has done a bit of work on it too. It's not really going very far at the moment, and the biggest problem is performance. The kernel already scales pretty well for CPUs, and kernel developers, thanks to Paul, have a pretty good handle on different locking structures. So maybe the transactional memory model is not that interesting. Andy did post a bunch of patches mid last year to sort of wholesale replace bin lock, spin unlock with hardware lock elision versions. He wasn't able to put performance numbers in there, but it didn't really get very far because of that, because he couldn't put performance numbers in. Also, to be fair to Andy, he probably didn't have his heart in it either. I don't think he sees this as probably the way forward. Andy did a really good talk in September at Plumbers last year, so if you're interested in this, probably read a little bit more, go and see his video on YouTube. Bless you. But maybe some of the more complex data structures that transactional memory is good at, where you have this ability to dynamically determine what your locking regions are, what is your shared data. So outside of the kernel, well, what about user space? Well, obviously you can just do this, right? So you can just use that in GCC. And eventually that will fall back to hardware transactional memory, and when it's supported in GCC on the different platforms, and in the meanwhile it'll use software transactional memory. If you want to know if your hardware actually supports it, x86 you can use CPU ID, PowerPC and S390 use the auxiliary vector, the hardware capability field in the auxiliary vector, and that'll tell you. So another interesting part is user space performance monitoring. So you want to profile these things, see what's actually happening with all of your transactions. And again, Andy Clean's been doing a whole bunch of work on this, and there's a whole bunch of, sorry, my slides seem to have stopped moving. There is a whole bunch of generic events that you can use. Unfortunately, the ones on the right are all hardware lock elision versions, which have no meaning on S390 and PowerPC, but Linux does tend to be very x86 centric sometimes, and this is kind of shown here. These are generic events that everyone's supposed to support. But anyway, you've got things like start, so you can profile on these events. So how many transactions did you start? How many committed? How many aborted? How many had a capacity overflow or a conflict? And then the last one here is the cycles. How many cycles did you actually, how many CPU cycles did you actually have inside transactions? That could be interesting for you. You can also get a bunch of information about the sample that you took. What was the state of the processor or the CPU at that time? Was it in a transaction? Was it in an elision, of course? Again, this is very x86 centric. We're hoping to plug a lot of this stuff in from the PowerPC side. We've got a lot of this information in the hardware in our performance monitoring unit. Tell you if a retry is possible and a bunch of other things. Branch filtering, x86 and Power support independently from transactional memory. You can log the number of the branches leading up to a particular performance monitoring event. So you can follow the code flow of your branches up until that point. And things that people want to do is often filter which branches they see, whether they're seeing conditional branches or calls or whatever. And you can do this with transactions as well on x86. You can say whether the branches were in transactions or not. And transactions aborts is an interesting one. So on x86, an abort is considered to be in a branch. So x86 don't have a register to say this is the instruction that I think caused the abort. But you can read it out of the branch log to say, I think this is where it aborted, and it'll tell you approximately where it is. So the other part is debugging. This is really tricky. This is really hard. And this is one of the reasons why we are seeing a lot of hardware support. You see all these registers in there for abort handling and where it happened and all that sort of stuff. So GDB is going to require some changes, and the S390 guys are doing a great job on this. They've already thought about a lot of these problems. And GDB needs to understand this change in code flow. It needs to understand you do a tier begin, and then you're kind of running for a while, and then it can end up at your abort handler, or it can end up at the X end. And so it needs to understand that. And one of the obvious ones is things like breakpoints and watch points. If you set a breakpoint in the middle of a transaction, philosophically, if it aborts, did it actually hit the transaction or not? Philosophically, but what will actually happen in hardware at the moment is it will hit the abort handler, and the hardware on x86 and S390, it'll roll it back to the start of the transactional, sorry, roll it back to the abort handler, and then GDB, it'll get past the GDB essentially at the abort handler, and the abort GDB will go, what the hell, I set a breakpoint over here and now I'm down here, what the hell's going on? So it may either kill the process thinking there's something wrong, or with, say, a watch point, it might go, that's not a load or a store, what am I going to do? I might retry then. I'm not sure what it'll do. It'll probably be architecture dependent. So with some of the work hopefully the S390 guys are doing, we'll be able to make a GDB that's TM aware and use some of these extra registers we've got. So we know that we've got a register on pretty much every platform that tells us where the abort was. If that's the same as the breakpoint you just set, then GDB can use that information to pass that back to the user and make some more informed decisions. Single stepping. Not really going to work. You can't single step it. You can't single step something with. Okay, you can single step. What's that, Paul?
I could ask a whole bunch of questions. I'll stick with one that's more on point. One thing you could do is single step by just having the neat internally set breakpoints as the instructions going through there and hoping that it goes the same way each time. Yeah,
so Paul's saying you could set breakpoints progressively through it and hope it makes its way through it the same process. You could do that, but of course the data may change and the program code.
It's really exciting if it took a different branch the next time. That's really
Yeah, exactly. And so the S390 guys the S390 guys are talking about even running it non-transactionally, but they'll marshal all of the other threads and sort of make them stop working, and hopefully there's no one else sharing that data that GDB doesn't have control of. I don't really like that solution at all because you're running non-transactionally then, so if you've got a self-induced abort or an buffer overflow abort, then...
The thing is, transaction memory is fairly simple enough that you just don't need a single step, right?
It's simple enough that you don't need to single step. Yeah, totally, yeah. I'm calling you when I hit bugs now. But,
With the suspend thing we have on power, one thing we would arguably do if we can't actually single step yet, see we can generate an injection block, we could run single step mode, record the PC, go back, record the PC, go back, record the PC, go back.
do it in suspend mode.
The kernel. We could have some special PoWER8 code to do that, and so we would basically run through the transaction using the single step hardware facility and essentially logging its instruction it goes through. So we will have a fast pass in
You're saying run it in suspend mode, or you're saying run it?
No, so every time we take a single step track, the hardware will suspend a transaction, go into the kernel. Then from the stop of the entry, we just log the PC and go back. Resume, execute an instruction, single step interrupt.
Okay, so Ben's saying it might be easier on, Ben's saying it might be easier on, Ben's saying it might be easier on power because we've got the suspend mode. We're not guaranteeing, of course, that once you suspend and come back, that it'll actually, that it will not board.
Full trace single step, that's too much. But we do a quick flat recorder. We could implement a special PoWER8 extension for that.
Oh, you're saying a very lightweight recorder that goes through and does it, so we don't go all the way to GDB. Yeah, okay. I still don't like the solution of doing that because you're still perturbing the transaction very easily. So you may end up with different results running it in, very different results running in GDB than not running it in GDB. That's always a problem with single stepping anyway. So anyway, let me move on. The one thing we do in PowerPC at the moment is we treat these things often as a single block. We do this with our larks, darks regions, where you basically enter the transaction and then you know that you turn off your single stepping there, and you'll either come out at the abort, at the abort handler, or at the end. And it's kind of a single block. Works okay with larks and stuff because they're fairly small regions, but with transactions we could be rather big, so it's going to be harder. S390 has the ability to trace the end of a transaction and trap into the kernel, so that'll be easier for them than it will for us and x86, but we'll see how it goes. And this is where I think simulators will be really, really useful. Intel have a simulator, we have a simulator, and things like QEMU you could use. That would enable you to actually single step through a transaction and not have to perturb it. Of course, simulators have their own problems and they don't exactly model the hardware, so you may have some problems there, some mismatch. Even if they did exactly match the hardware, you'll always have timing problems as well. So it might be useful for some certain subsets of problems. So yeah, except you could just call up Paul now and he'll debug your transactions for you.
If you have a single step in your transaction really too big, just make it small.
Paul's saying if it's too big, just make it smaller. Yeah, okay. If you listen to some people, transactions will be infinitely big soon, so yeah. Okay, anyway, as Paul always says, this is sponsored by the IBM Legal Department, and that's it. Thanks. Do we have any more questions?
Thank you, Michael. We've got time, a couple of minutes for additional questions.
Yes?
Yes, so you said the mechanism of rollback is just to use the caching mechanism and invalidate the cache lines that conflict or that are in the transaction. Presumably then that means that an aborted transaction is also a performance hit because you need to go and refetch, refill your caches. Is that measurable on workloads or is it not true?
So you're saying that you have to you invalidate those cache lines when you do an abort. Yes and no. It depends on how it's implemented in the cache. You actually keep two copies if you wanted to. So you could have one that's, when you read a value, you keep it in one cache line, and then when you write a transaction, you can keep it in another cache line, and you can just invalidate the one that you wrote and keep the written one around. Of course, that'll have its own performance implications because you're now using more cache. Yep. So caches are also set associative, is what Ben's saying, so that would also have problems with overflowing your caches. I don't know the answer to would that actually have any performance problems. Yes, possibly, but hopefully the higher level optimization of transactional memory and being able to dynamically determine where your shared data is will help more than that would actually hurt. But yes, there is definitely potential for performance losses with this, absolutely. No. Oh, sorry.
Examples where you have performance gain actually by the use of transactional memory.
Examples
Is
of
there any practical uses where there is a positive effect on this? I've tried numerous times, proprietary software as well kernel software, to use this, and nothing really give me any advantage.
So are there any uses, Christoph, are there any performance improvements?
Yeah, it's just exercise for the mind, okay. I like academics, but what is this about?
I think it's hard for us kernel developers to answer that question because we're all pretty smart anyway. So and you know, modest. It's a. I think if you're trying to, okay, Paul, want to answer that question?
Sure. From what I've seen, the cases that work best right now are cases where you have a large data structure that has no real nice way to partition it. The kind of the textbook examples. Like
Yeah, that's what Intel gives us as an example to justify this. I've never seen something like that work in reality, though. I've had my C developers, user space, work on these solutions, and they came up with this doesn't work. They never were able to get any improvement in performance using these techniques.
So just to repeat what you said, Paul said basically the large data structures where you can easily dynamically determine where, it's more easily to dynamically determine where the shared data structures are.
What the deal is that what you need to do, you have to be a little careful. If you just blindly do a transaction around an update of our B tree, you're going to nail the whole thing down from the
Right.
where you are.
I'm very well aware of these.
That's okay if you're doing modifications to different parts of the tree because they're only up there.
But we have this example, for example, in this lab allocators. We have this partial list where you have to do these insertions. And Andy has spent, I think, six months on trying to optimize this. And he never came up with anything on that one as well.
The thing is that you aren't required to use transactional memory on its own. I mean, you can if you want to, but you aren't required to.
Yes. Okay. I wish there would be something.
So one of the things you could do would be to use RCU to track down until you nail things down until you get to the part where you want to modify. And use a transaction just on that little part of the tree. And then your footprint's smaller and you have a chance of it working.
And at that point, probably some other atomic operation will be more effective because you have a significant overhead by starting a transaction at any transaction.
I don't think you're going to have a single atomic transaction that's going to rebalance an RB tree. But
No, but you have to come up with an addition and the data structure where you have this limited change where you can just change a word and so forth.
if you have free choice of data structures and you pick a hash table or a radius tree or something that's partitionable, I have a hard time believing the transaction memory will win. We asked the question where if I win, I was giving you that.
Starting with transaction as a large case.
Anyway, I won't summarize that, except Paul said advocated for RCU. So.
Yeah, on behalf of the conference gift of the towel, please join me in thanking Michael again for the talk.